Section: Introduction. In this section, we explore a promising method for using foundation models, particularly large language models, LLMs, by viewing them as general-purpose decision-making agents. For an LLM agent to be effective, it must do more than just provide reasonable responses to input text. It needs to engage in interactive, goal-oriented behavior to complete specific tasks. This involves mastering two key aspects. First, generating responses that actively seek information about the task, and second, making decisions and refining them through a process of thinking and verification during inference. For example, when working with a new coding library, a successful LLM agent should start by creating programs, then test the most promising ones with a compiler, use the feedback to enhance the program, and repeat this process multiple times. The ability to improve responses through successive attempts is akin to a form of self-improvement during testing. To facilitate this self-improvement at test time, recent strategies have focused on leveraging the knowledge embedded in pre-trained models through few-shot prompting. While prompt tuning combined with feedback can lead to better responses from capable models, it often falls short in enabling models to correct their own mistakes, especially in complex tasks that require logical reasoning. In many cases, models possess the necessary knowledge to tackle difficult prompts but struggle to access that knowledge, even when prompted to correct their errors sequentially. Fine-tuning the LLM on specific question-answering data can help, but it does not equip the agent with a strategy for improving its responses during testing. Developing a method for enhancing responses over multiple attempts is essential for addressing challenging prompts, where trying to solve the problem in one go may not be effective. We ask ourselves if we can train models to enhance their own responses. If we succeed, this could provide LLMs with a general approach for tackling difficult prompts by improving themselves, rather than relying on direct supervision about what to say, which may not apply when the test prompt is different from the training data. One straightforward way to instill this capability in a model would be to create data that illustrates improvements over several turns, potentially sourced from highly capable models. However, we find that merely mimicking this data is insufficient for developing this ability. There are two main reasons for this. First, multi-turn data from a different model may not address the specific errors the learner makes, making it irrelevant. Second, sequential multi-turn data from proprietary models often lacks quality, as these models may not effectively suggest meaningful improvements to their own mistakes, even if they can still provide useful answers. Thus, we need a new strategy to give models self-improvement capabilities. Our key insight is to guide the learner's improvements iteratively, drawing inspiration from online imitation learning and reinforcement learning methods. This guidance can come in the form of ideal responses to prompts sampled independently from more capable models or generated by the learner itself. Our contribution is an algorithm called RISE, Recursive Introspection, which uses these insights to enhance the self-improvement capabilities of an LLM over multiple attempts at a given prompt. In each iteration, our method builds on the learner's responses, generating better answers for the next turn by selecting the best options from multiple revision candidates, either from the learner or a more capable model, depending on what is more effective. By doing this, we create rollouts that show the learner how to improve its responses based on its own distribution. We then fine-tune the learner using a reward-weighted regression objective, which allows it to learn from both high and low-quality parts of these rollouts. By repeating this process iteratively, we instill a general self-improvement capability in the LLM. Our results indicate that LLMs trained with RISE can provide correct answers to more prompts, showing improvement over multiple attempts, especially for challenging ones. Even though strong base and instruction-tuned LLMs often struggle to enhance their responses over several attempts, RISE successfully equips similarly sized LLMs with self-improvement abilities, leading to consistent performance gains after each turn. For instance, on the GSM-8K dataset, RISE shows significant improvements across various models, enhancing the performance of Llama 3 to 8B by 8.2% and Mistral 7B by 6.6%, using only their own data. RISE achieves a 17.7% improvement for Llama 2 to 7B over 5 turns and a 23.9% improvement for Mistral 7B, while GPT 3.5 only improves by 4.6% over the same number of turns. We observe similar patterns in the math dataset, where RISE boosts Llama 2 to 7B by 4.6% and Mistral 7B by 11.1% over 5 turns. We also investigate how RISE fosters self-improvement abilities and demonstrate that this capability generalizes to prompts outside the training distribution. These findings consistently highlight RISE's effectiveness in enhancing mathematical reasoning skills across different models. Section Summary. In this section, we explore the concept of training large language models, LLMs, to function as self-improving agents capable of enhancing their responses through iterative feedback and decision-making. We introduce our algorithm, RISE, Recursive Introspection, which enables LLMs to learn from their own responses and improve performance on challenging tasks, demonstrating significant advancements in accuracy across various datasets compared to existing models. Section: Related Work. In this section, we explore related work that has aimed to enhance the reasoning and thinking abilities of foundational models for various applications. Many of these studies focus on developing prompting techniques that facilitate effective multi-turn interactions with external tools. They often refine predictions by reflecting on previous actions, encouraging the model to articulate its thoughts, prompting it to critique and revise its own outputs, or employing other models to evaluate the responses of a primary model. While some of this research does lead to improved responses, the ability for self-correction frequently depends on having access to detailed error information, such as execution traces from code compilers. Our findings, along with the data presented in our tables, suggest that self-improvement driven by the model itself, referred to as intrinsic self-correction, is often not feasible for standard large language models, LLMs, even when they possess the necessary knowledge to address a given prompt. However, we demonstrate in this paper that fine-tuning with our method, RISE, can enable this capability. Beyond prompting, earlier studies have also sought to fine-tune LLMs to develop self-improvement abilities. These efforts typically aim to enhance reasoning performance by training the models on responses they generate themselves. To achieve this, they utilize a mix of learned verifiers, search techniques, contrastive prompting with negative examples, and iterative supervised or reinforcement learning. While our approach also involves training on data generated by the model, our goal is to introduce a complementary ability that enhances performance across multiple turns of interaction, rather than focusing solely on improving performance in a single turn. Some research has fine-tuned LLMs for multi-turn interactions directly through reinforcement learning. Although this is related to our work, we recognize that single-turn challenges within multi-turn contexts present different issues compared to general multi-turn reinforcement learning. Specifically, in our case, sample efficiency is not a concern since the entire environment is defined by the training dataset of prompts and correct answers, and the dynamics are predictable. Additionally, we need to ensure that the model can generalize to new test prompts. While multi-turn reinforcement learning emphasizes sample efficiency, we find it appealing to learn how to generalize from a limited number of initial states. Our primary focus is to demonstrate that we can train models for self-improvement by carefully designing multi-turn fine-tuning objectives. This focus is independent of the training method used, whether it involves reinforcement learning or not. The works most closely related to ours are GLORE and Self-Correct, which train separate models to identify errors and refine the incorrect answers of other LLMs. In contrast, our approach trains a single model to generate answers and improve them over more than 2 turns, which is the maximum number of turns explored in those studies. We show that achieving this successfully requires thoughtful design choices, including an iterative on-policy data generation strategy and a training objective that learns from both successful and unsuccessful attempts. From an algorithmic perspective, RISE is akin to online imitation learning, as it seeks expert guidance on states reached through on-policy rollouts. On-policy distillation for LLMs employs a similar concept but asks an expert to provide completions for partial responses rather than for sequential attempts, which is what we do in our work. Now, regarding our problem setup and preliminary considerations, our goal is to enhance LLM performance across sequential attempts at solving a given problem. Specifically, we aim to develop an LLM that, when presented with a problem, previous attempts at that problem, and additional instructions, such as guidance to identify mistakes and improve responses or feedback from the environment, can solve the problem as accurately as possible. To achieve this, we encode our objective into a learning goal that we seek to optimize. Unlike traditional supervised fine-tuning, which trains the model to produce a single response for a given problem, our approach trains the model to appropriately respond to a history of its previous attempts. This objective closely resembles a reinforcement learning goal, and we will indeed adapt our method by transforming a single-turn problem into a multi-turn Markov decision process. Finally, we note that prompting-based methods, like self-refine, can also be seen as training the model to optimize its responses, but they only allow for adjustments to the prompt to achieve this optimization. Since the model's parameters remain unchanged, this approach may not fully optimize the objective we are targeting. In summary, we are developing RISE, a method for fine-tuning foundational models to enhance their ability to improve their predictions over multiple turns. Our approach involves converting a problem into a multi-turn Markov decision process, collecting relevant data, and then applying offline reward-weighted supervised learning within this framework to foster this self-improvement capability. Section Summary. In this section, we discuss our approach, RISE, which aims to enhance the self-improvement capabilities of foundation models by fine-tuning them to improve their predictions over multiple turns in a structured manner. We convert problems into a multi-turn Markov decision process, MDP, and utilize offline reward-weighted supervised learning to effectively train the models to refine their responses based on previous attempts. Section: Converting single-turn problems into a multi-turn Markov decision process, MDP. In this section, we outline how we convert single-turn problems into a multi-turn Markov decision process, or MDP. Our first step involves creating a multi-turn MDP from a dataset that includes prompts and corresponding Oracle responses. For instance, we might have a dataset consisting of math questions and their natural language answers. From this dataset, we construct an induced MDP and then learn policies within this framework. In our MDP, an initial state represents a possible prompt. We refer to the output response generated by our model as an action. When we are in a certain state, we can determine the next state by combining the tokens that represent the current state with the action suggested by the model, along with a fixed prompt that encourages the model to reflect on its response. For example, we might ask the model to reconsider its answer by saying, "This response is not correct, please introspect and correct your answer." The reward function we use is a simple binary indicator that tells us whether the answer is correct at a given state, based on an answer checking function. Next, we focus on learning within this multi-turn MDP. With the MDP set up, we train the model to enhance its performance over time. We take an offline approach to learning, which we will explain in detail. Step 1 involves collecting data for self-improvement. To ensure that the data we gather from the multi-turn MDP is beneficial for teaching the model, it must meet several criteria. It should highlight the mistakes the model is likely to make and show how to correct them in future attempts. It should provide responses relevant to the model based on the problem and previous attempts, and it should not include any rollouts that worsen in later turns. Our data collection strategy meets these requirements. In each round, for a specific problem, we run the current model to generate multiple sequential attempts. If there is external input available, such as feedback from a compiler, we also gather this information. We also track a reward value associated with each attempt. We refer to this dataset of on-policy model rollouts as our collection of data. For each time step, we create an improved version of the response and record the reward score linked to this enhanced response. To improve a response, we can use several methods. One straightforward approach is to ask a more capable model to provide a correct answer based on the prompt, the previous response, and any external feedback. We call this the distillation variant of our method, as it uses a strong teacher model to guide the self-improvement process. This differs from the traditional concept of knowledge distillation, and we will clarify these differences in later sections. The second variant, which does not require a teacher model, involves generating an improved response by sampling multiple times from the learner itself. We refer to this as the self-distillation variant. Specifically, for each state in our dataset, we sample 4 responses and select the best one based on the associated reward values to relabel the model's response in the next step of the improvement process. Step 2 focuses on policy improvement. With our data construction methods in place, we can now train a model using these datasets. While we could use any offline reinforcement learning approach, we choose a method based on weighted supervised learning for its simplicity and ease of experimentation. We perform a weighted supervised regression, where the weights are determined by the exponential transformation of the reward values. We also introduce a temperature parameter to adjust the differences between good and bad actions. In our initial experiments, we noticed that this approach could lead to a bias towards increasing the likelihood of responses that received high rewards, which tends to prioritize easier problems. To counter this, we modify our approach slightly by centering the exponentiated rewards around the mean value across all attempts for a given prompt, similar to advantage-weighted regression. We find that using advantages instead of raw rewards helps us avoid the issue where easier problems continue to dominate the learning process. Section Summary. In this section, we describe our method for transforming a single-turn dataset into a multi-turn Markov decision process, MDP, to facilitate self-improvement in model responses. We outline our data collection strategy to ensure that the generated rollouts effectively illustrate mistakes and improvements, and we detail our training approach, which employs both teacher-guided and self-distillation methods to enhance the model's performance through weighted supervised learning. Section: Inference at Deployment Time. In this section, we explore how RISE operates during deployment. RISE can function in 2 different modes when making predictions. The first and perhaps simplest method involves running the policy trained by RISE in a multi-turn rollout. Here, the model generates a new response based on the previous context, which includes external feedback about the last response. We stop this process as soon as the current response is deemed correct according to the environment's answer verification system. In other words, we end the rollout when the reward for the current response matches the reward for the ideal response. This method requires us to query the reward function after each turn, so we refer to it as the with Oracle approach. Alternatively, RISE can operate in a mode that does not require us to check the answer or query the reward function during the rollout. In this scenario, we conduct full-length rollouts by having the model attempt responses multiple times, regardless of whether they are correct. We then use a self-consistency method based on majority voting to determine the best response at the end of each turn. Specifically, at the conclusion of each turn, we identify the response by conducting a majority vote among all response candidates from the previous turns, including the current one. We call this approach without Oracle. We illustrate these methods in a figure, and most of our evaluations utilize the without Oracle method. Next, we provide practical details about our algorithm and its implementation. We present complete pseudocode for each approach in the appendix. We trained models with 7 billion parameters using RISE and discovered that these models often struggled to maintain the desired response style and follow instructions for improving their outputs when generating data on policy. Therefore, before we collect on policy data, we find it beneficial to conduct an initial phase of supervised fine-tuning using in-domain, multi-turn rollouts generated from a capable model. This phase, which we refer to as the knowledge boosting stage, helps provide the learner with style and instruction following information. After this, we proceed with on-policy rollouts starting from the boosted model. In each iteration, We generate one trajectory for each unique problem and then perform fine-tuning, with specific hyperparameters and details available in the appendix. For iterative fine-tuning, we find that beginning with the base model and training on data from all previous iterations is more effective than continuing fine-tuning from the last checkpoint. We also address the question of why self-improvement with RISE is possible. One might think that if the model cannot answer correctly on the first attempt, it may lack the knowledge to correct its mistakes. However, we explain why this self-improvement is feasible, supported by empirical evidence. Teaching a model to update its responses iteratively can be essential when the target distribution requires more capacity than what the model can achieve by only considering the input prompt tokens. When the target distribution demands greater capacity, learning a series of conditional probabilities followed by marginalization can lead to a more flexible overall distribution. This idea is similar to the difference between diffusion models and variational autoencoders in image generation. Diffusion models iteratively fit a series of generative distributions over noisy inputs, resulting in a more adaptable distribution compared to traditional variational autoencoding, even though both methods use a lower bound objective. To test our hypothesis, we monitored the training of the unweighted negative log likelihood loss for the ideal response given the input prompt, averaged over intermediate steps in a multi-turn rollout. We compared this with the loss values obtained by directly predicting the final response. Specifically, we sampled 256 prompts and their ideal responses, calculating the average loss across all prompts, along with a 95% confidence interval for different training checkpoints. We found that for any number of training epochs, the loss was lower when conditioning on the multi-turn data generated by RISE compared to the ideal responses from an expert. This indicates that RISE effectively uses information from previous turns to model the target distribution. We also measured the average loss across all samples during training, comparing RISE with traditional fine-tuning, and observed a similar trend. RISE consistently reduced loss more effectively, achieving lower perplexity values. However, in cases requiring knowledge-based question answering, the model may not improve meaningfully because its learning is limited not by capacity but by the absence of critical features needed to map inputs to correct outputs. In such scenarios, we expect that training with RISE could lead to hallucinations, as more input tokens from previous attempts might encourage the model to pick up on misleading correlations. Nevertheless, this is not the case for reasoning problems, where we find that the performance at the first turn is often better than the performance at the first pass, suggesting that the model can improve by sampling itself. In fact, we demonstrate that the sequential learning process developed by RISE can solve many problems that were not resolved by larger models in the first turn, indicating that it learns to access the pre-trained knowledge of the model in a more effective way than simply translating performance metrics from single-turn approaches. Section Summary. In this section, we describe two modes for running RISE during inference, with Oracle, which queries a reward function after each response to ensure correctness, and without Oracle, which relies on majority voting from multiple response attempts. We also discuss the importance of a knowledge-boosting phase for improving model performance and provide empirical evidence that RISE enables self-improvement by leveraging multi-turn data to better model target distributions, particularly in reasoning tasks. Section: Experimental Evaluation. In this section, we aim to showcase the effectiveness of RISE in helping language models enhance their responses over multiple turns. Our experiments focus on several key questions. 1. How well does RISE improve performance across several attempts at the same prompt? 2. Does RISE's performance get better with more rounds of training? 3. Can the self-improvement strategy from RISE be applied to new problems outside of the training scope? And finally, 4. What is the optimal data setup for training RISE? To explore these questions, we compare RISE with other existing methods and conduct tests on the GSM-8K and math datasets. We look at various baseline approaches that also aim to foster self-improvement, including A. Self-refine, which encourages a base model to identify and correct its own mistakes. B. GLORE, which uses a separate reward model to find errors and a refinement model to enhance the responses of a base language model. and C. Self-consistency, which employs majority voting on multiple responses from the first turn as a baseline for our sequential method. We strive to make fair comparisons by using models of similar sizes, but differences in the base models, training data, and evaluation methods sometimes prevent us from making direct comparisons. Nevertheless, we can still gain insights into the level of improvement by relating our findings to these previous works. We also compare RISE to V-star, but since this isn't a fair comparison, we will discuss it in the appendix. We evaluate RISE in two scenarios during inference, with and without an oracle at the end of 5 turns. Specifically, we define our metrics as follows. With oracle, we measure performance by stopping the process as soon as the response is correct, allowing for checks against the final answer verifier at the end of each turn. Without oracle, we continue through all 5 turns and calculate the performance based on the best candidate responses produced at each turn. We also assess the performance at the first turn for all models we train. Now, regarding whether RISE enhances performance over multiple turns compared to other methods, we present our findings in a table. Notably, RISE significantly boosts the performance of the Llama 2 base model over 5 turns, achieving improvements of 15.1% and 17.7% on GSM-8K, and 3.4% and 4.6% on math, without any oracle assistance. Interestingly, we observed that using self-refine alone tends to lower performance, even with a strong model like GPT-3.5. The top-performing 7B models, Mistral 7B and EURUS 7BSFT, show only modest improvements of 5.3% and 11.6% on GSM-8K, and 0.9% and 4.0% on math, which are significantly less than what we achieve with RISE. GLORE shows a slight improvement of 3.4% on GSM-8K over 2 turns, but this still falls short compared to RISE, which improves by 6.3% in 2 turns and 13.4% in 3 turns. In summary, training with RISE yields the most substantial performance gains compared to other methods, both with and without oracle support, and these benefits extend to other base models. One might speculate that the improvements we see with RISE are mainly due to using queries from a more capable model for guidance rather than the specific algorithmic approach for data collection and training. To test this idea, we saved all the data generated by RISE from these more capable models and trained on it using standard single-turn supervised fine-tuning. Since not all this data is guaranteed to be correct, we also conducted experiments using only the correct responses from the oracle data. Our results indicate that this method does not effectively instill self-improvement capabilities, often maintaining or even degrading performance compared to simply sampling one response in the first turn. This suggests that the design of the RISE algorithm is crucial for enabling self-improvement, rather than relying solely on expert supervision. Section Summary. In this section, we evaluate the effectiveness of RISE in enhancing language models' self-improvement capabilities across multiple turns, finding that RISE significantly boosts performance compared to other methods, achieving up to 17.7% improvement on GSM-8K without an oracle. Our results indicate that the algorithmic design of RISE is crucial for instilling self-improvement abilities, as simply using data from more capable models does not yield the same benefits. Section. Does the performance of RISE improve with iterative training? In this section, we explore whether RISE improves with multiple rounds of training using on-policy data. Our findings, as shown in the tables, indicate that RISE's performance consistently enhances with each iteration. Specifically, the performance after 5 turns, both with and without an oracle, shows a noticeable improvement as we increase the number of training rounds. This suggests that we can combine iterative self-training methods, like STAR, with RISE to enhance model self-improvement. It also hints at the potential benefits of fully online reinforcement learning techniques. Next, we assess whether RISE can enhance sequential performance on prompts that are out of distribution. In our table, we aim to evaluate how robust the strategy developed by RISE is when faced with new, unseen prompts. We compare the performance of the RISE model trained on one dataset against evaluation prompts from another dataset, which includes math, GSM-8K, and SVAMP. Generally, we observe that a model trained on one dataset can still improve the base model's performance on a different dataset over 5 sequential turns. More specifically, while the base Llama 2 model tends to perform worse in the 5th turn compared to the first, models trained with RISE show a positive performance increase on these out-of-distribution prompts. This indicates that even without prior exposure to similar queries, training with RISE on certain mathematical prompts can enhance the effectiveness of the self-improvement strategy on a new set of test prompts. This finding suggests that RISE can foster self-improvement methods that generalize beyond the prompt distribution in the fine-tuning data. We then investigate how different data compositions impact RISE's performance, aiming to answer questions about whether we should gather on-policy error correction data, like Dagger, or focus on high-quality off-policy data. To understand the value of various data compositions, we consider 3 aspects of RISE. A. Using multi-turn rollout data for fine-tuning. B. Employing unsuccessful or suboptimal rollouts through weighted supervised fine-tuning instead of just using successful rollouts. And C. Utilizing on-policy rollouts along with self-generated or Oracle data. We will conduct controlled experiments to assess how each of these factors influences RISE's overall performance. For A, we first examine the importance of incorporating error correction history in training RISE. We compare 2 methods. One where the model is trained with Oracle answers provided immediately after the query, referred to as one turn, and another where Oracle answers are given after intermediate failed attempts, called multi-turn. Our results show that the multi-turn approach, despite training on responses that may not always be correct, achieves better performance than training solely on the correct response for a given prompt. This underscores the significance of training on contexts that include a history of multi-turn interactions, which can enhance self-improvement capabilities. For B, we explore the impact of reward-weighted reinforcement learning on multi-turn data in RISE compared to simply imitating filtered successful data. We find that utilizing all available data leads to better performance than just filtering for successful examples, which reduces the sample size. Our findings indicate that reward-weighted training enhances performance in later turns, allowing us to make better use of all suboptimal data. For C, we analyze the differences between on-policy and off-policy data, as well as self-generated versus expert data. RISE operates on policy rollouts and seeks to improve the responses generated by the learner. Our results show that a Dagger-style approach, which focuses on improving responses from on-policy rollouts, yields better performance compared to relying solely on expert data. This approach addresses the mismatch between training and testing distributions, enabling imitation learning methods to target the correct distribution. Additionally, recent studies suggest that large language models often memorize unfamiliar examples generated by Oracle models. By training on policy rollouts, we can mitigate these potential issues. While models trained through offline imitation can reduce loss, these improvements do not generalize to new problems. Finally, we examine the performance of sequential sampling with Oracle feedback in GSM-8K, as opposed to relying on majority voting. We compare RISE's performance with early termination of evaluation rollouts against the pass at 5 performance of the RISE model at the first turn, which makes an equal number of queries to the ground truth correctness indicator. We expect that access to the ground truth correctness indicator will enhance performance for both parallel and sequential sampling. However, our results indicate that RISE improves performance beyond simply sampling more responses at the first turn and calculating pass at K, despite the strong assumption of having access to an Oracle final answer verifier in the parallel sampling approach. We anticipate that parallel sampling via pass at K would perform best when given access to Oracle answer checking, as the model can choose to sample multiple independent responses if the base model's accuracy is reasonable. Pass at K at the first turn also sets an upper limit on the first turn accuracy of any method that does not query the Oracle. In contrast, Sequential sampling generates correlated samples and should not, in theory, outperform parallel sampling unless the model can effectively utilize the additional tokens and computation provided by the feedback self-improvement prompt. Since the sequential performance of the model exceeds the parallel performance, this indicates that RISE successfully achieves this improvement. Section Summary. In this section, we demonstrate that RISE consistently improves its performance with iterative training on policy data, suggesting its compatibility with self-training methods like STAR. Additionally, we find that RISE enhances sequential performance on out-of-distribution prompts, indicating its ability to generalize self-improvement strategies beyond the training data. Section: Error Analysis of RISE Overturns. In this section, we conduct an error analysis of the improvements made by RISE without any oracle feedback. Our goal is to understand how the rates of incorrect and correct responses change over multiple turns when we do not use an oracle for early termination. We illustrate our findings using Venn diagrams. First, we observe a steady increase in the number of problems that remain correct and a steady decrease in those that remain incorrect. This indicates that as we increase the number of turns, our model is able to answer more problems correctly. Second, we notice a consistent decline in the number of problems that shift from being correct to incorrect, which is not typically seen in strong proprietary language models like GPT. Additionally, we find that the total number of incorrect problems that turn correct in the next turn decreases. This is a direct result of the shrinking set of incorrect responses as more problems are answered correctly over turns. This suggests that we can achieve intrinsic self-improvement through fine-tuning with RISE, even without external input during evaluation. We also examine several examples from the GSM-8K test set to qualitatively analyze RISE's behavior over turns and identify various patterns, which we present in the appendix. For example, the trained model might completely rewrite its previous answer if it was entirely incorrect to arrive at the correct solution, or it may make minor adjustments if the previous answer was mostly correct. Another notable pattern is the model's ability to identify errors in its earlier responses and refine only the incorrect parts. Furthermore, the model shows resilience to noisy feedback from the environment when there is no oracle-assisted early termination. In our discussion of RISE, we highlight that it is an approach for fine-tuning language models to enhance their responses over multiple turns. RISE employs an iterative reinforcement learning strategy based on policy rollout data, using either expert or self-generated supervision to guide self-improvement. We find that RISE significantly boosts the self-improvement capabilities of 7 billion parameter models on reasoning tasks like GSM-8K and math, achieving improvements over turns that previous research has not seen in strong proprietary models. Moreover, RISE surpasses earlier methods aimed at similar refinement and correction challenges, while being simpler since it operates effectively with just one model instead of multiple. Despite these promising results, we acknowledge several open questions and limitations. Due to computational constraints, we were only able to perform 2 iterations of training with RISE, and just 1 iteration when the supervision comes from the model itself. Enhancing self-generated supervision will likely require more computational resources and additional iterations, as it is slower than using an expert model. RISE necessitates manual iterations, so developing a more online version of RISE may be the long-term solution, especially for scaling on policy learning efficiently. Additionally, while our work focuses on fine-tuning models for one task at a time, it would be intriguing to incorporate data from the protocols outlined by RISE into broader instruction tuning and post-training processes. Given that fine-tuning with RISE data does not negatively impact the first-turn performance of any model we trained, we hypothesize that integrating this type of data into general instruction tuning pipelines should also be beneficial, while enabling the sequential self-improvement capability that is largely missing in current models. We would like to acknowledge that this work was conducted at CMU. We express our gratitude to Fahim Tajwar, Abatha Thankaraj, Amrith Settler, and Charlie Snell for their valuable feedback and discussions. This research was supported by ONR under a specific grant number, OpenAI Super Alignment Fast Grants, and utilized the Delta system and Jetstream 2 at the National Center for Supercomputing Applications through other grant numbers, which were supported by the National Science Foundation. We also thank OpenAI for providing credits for academic use of GPT-4.